Welcome to this look at the reality of economic data. In textbook statistics, we often assume homoskedasticity, the idea that our error terms have a constant variance, creating a neat tube of data points. But real-world data is rarely that well behaved. Take this chart of household income versus food expenditure. As income increases, notice how the spread of data points widens into a fan shape. This is heteroskedasticity. Formally, we define it as the variance of the error term, conditional on our independent variables, not being equal to a constant sigma squared. For economists, this isn't just a technicality, it's a reflection of human behavior. While low-income families have very constrained spending on food, wealthier families have much more choice, leading to greater volatility in the data. Understanding this variance is crucial because it directly impacts the reliability of our statistical models. This flowchart outlines the systematic approach to handling heteroskedasticity in econometric analysis. We begin with a standard OLS regression using the regress command. The first critical step is diagnostics, which includes both visual inspection using rvfplot to look for patterns and residuals, and formal testing via estat hettest. The decision point rests on the p-value of these tests. If the p-value is greater than 0.05, we assume homoskedasticity and proceed to interpret our OLS results. However, if the p-value is less than 0.05, heteroskedasticity is detected, and we must choose an appropriate remedy. These remedies fall into three categories: the agnostic approach using robust standard errors with the VCE robust option, a structural approach where we explicitly model the variance using het-regress or weighted least squares, or a specification check involving data transformations, such as taking the log of variables. This slide provides a decision matrix for selecting the most appropriate tool in Stata when encountering heteroskedasticity. We compare three main methods: robust standard errors, modeling variance, and generalized least squares. For general-purpose use, where the form of variance is unknown, robust SEs using the VCE robust option are recommended because they are easy to implement and model agnostic, although they only address inference and are not fully efficient. If the variance is central to your research question, such as in risk analysis, modeling it directly with commands like heteroregress or VWLS can gain efficiency and explain volatility, though this approach is sensitive to model misspecification. Finally, for panel data involving cross-sectional time series, XTGLS handles complex error structures but typically requires a large time dimension. Ultimately, your choice should balance the need for efficiency against the risk of misspecification. Let's look at the mathematical mechanism behind breaking the Gauss-Markov assumptions. On the left, we have the ideal assumption, homoskedasticity. Here, the variance-covariance matrix, omega, has a constant sigma squared value across all diagonal elements, representing a uniform spread of error. On the right, we see reality, heteroskedasticity. In this case, each observation has its own unique variance, denoted by sigma sub I squared. This variation on the diagonal directly impacts our results. First, standard errors become biased because OLS formulas assume a single constant variance. Second, this leads to invalid inference. Your T-stats and F-stats can no longer be trusted. Finally, OLS loses its efficiency, meaning it is no longer the best linear unbiased estimator, or BLUE. Understanding this matrix shift is key to diagnosing and fixing these issues in your models. When heteroskedasticity is present, it's essential to understand its specific impacts on our model. On the left, we see what remains valid. Our coefficient estimates are still unbiased and consistent. This means the regression line still captures the central tendency of the data correctly. However, on the right, we see what breaks. The standard errors are now biased because OLS treats all observations as equally weighted, despite their different variances. This leads to invalid inference. Confidence intervals become unreliable, often appearing narrower than they should be, and p-values become misleading, which increases our risk of a type 1 error. Ultimately, while OLS remains unbiased, it loses its status as the most efficient estimator, or blue. Heteroskedasticity is more than a mathematical problem. It is a window into human behavior. Look at this scatter plot of income versus consumption. At low income levels, we see constrained choice. When necessity dictates every dollar spent, variance is naturally low. But as income grows, choices expand. High-income individuals can choose to save or splurge on luxury, leading to the high variance we see in the expanded choice zone. This fan-shaped pattern reflects three core economic principles: the scale effect, where larger entities exhibit larger fluctuations; the learning curve, where experience brings more consistent outcomes; and discretionary income, which multiplies behavioral options. By understanding that variance is information, not just noise, we can derive much richer interpretations from our economic models. Now, let's look at how to put this into practice using Stata. We start by loading the built-in auto data set and describing our variables, price and miles per gallon. Step 2 is running a standard, baseline OLS regression to establish our starting point. In Step 3, we visually inspect our errors using rvfplot. Adding a horizontal line at 0 makes it much easier to spot any fan-like patterns in the residuals. Finally, if heteroskedasticity is a concern, we apply what researchers often call the magic option, adding VCE robust to our regression command. This robust flag tells Stata to use the Huber-White sandwich estimator, which corrects the standard errors for heteroskedasticity while leaving the coefficient estimates themselves unchanged. It's the most widely used remedy to ensure your t-statistics and p-values remain valid in the presence of non-constant variance. Standard robust errors are the default choice for large samples, typically where n is greater than 250, as they remain agnostic to the form of variance. For small samples under 50, or datasets with high leverage points, using HC2 or HC3 is critical, with HC3 providing a more conservative approach. For grouped data, such as students within classes, clustered errors are necessary to correct for correlation within those groups. For instance, using HC3 for a dataset with only 30 observations ensures more conservative and valid inference. Beyond simple correction, we can also model the variance structure directly. Let's look at a concrete case study, modeling household food expenditure as a function of income. We start with what we call a naive OLS model. On the right, you see the standard Stata regression output. While the coefficients look straightforward, notice the highlighted standard errors. We label these suspect because, in economic theory, we expect food spending to be more volatile for high-income families. This suggests our constant variance assumption might be violated, making these standard errors potentially unreliable for hypothesis testing. We always start with a visual check of the residuals to see their shape. An expanding fan shape is a classic sign that variance scales with fitted values. We use the rvfplot command in Stata to generate this visualization. For example, notice the residual spread widens significantly as the fitted values on the x-axis increase. Visuals are great, but we need a formal test to be sure. To move beyond visual inspection, we use the Breusch-Pagan test, executed in Stata with the command estat hettest. The null hypothesis, or H0, for this test is homoskedasticity, or constant variance. In our output, the chi-squared statistic is 14.28, which yields a p-value of 0.0002. Since this p-value is significantly less than our alpha of 0.05, we must reject the null hypothesis. This provides formal statistical evidence that heteroskedasticity is present in our model for food expenditure. To address heteroskedasticity, we use robust standard errors, implemented in Stata by adding the VCE robust option. As shown in the comparison table, the coefficient for income remains exactly the same at 0.48. This confirms that OLS coefficients are still unbiased despite the heteroskedasticity. The real change is in the standard errors, which increase from 0.05 to 0.09 to reflect the true level of uncertainty in the data. Because the standard error is now higher, our t-statistic becomes more conservative, falling from 9.60 to 5.33. This ensures that our hypothesis tests and conclusions are much more reliable. Instead of simply correcting standard errors and treating variance as a nuisance, we can use the het-regress command to model it directly. This moves us from mere correction to explanation. In this example, the variance equation shows a positive coefficient of 0.002 for income, confirming that volatility in food expenditure increases as income rises. A key benefit is that maximum likelihood estimates are more efficient than OLS, meaning they provide smaller standard errors, provided that your variance model is correctly specified. Think of this as estimating not just the average spending, but also the spread or uncertainty of that spending as a function of income. Sometimes, however, the issue isn't just variance, it's the functional form itself. Let's look at log transformations next. Sometimes heteroskedasticity is more than just a statistical nuisance. It is often a symptom of using the wrong functional form. Let's compare these two plots. On the left, the linear scale plot of price versus square footage shows clear heteroskedasticity, with the data points fanning out as house size increases. However, on the right, by log transforming both variables, we achieve two major improvements simultaneously. We stabilize the variance and improve the linearity of the relationship. This log-log model is a powerful tool for modeling proportional changes. As seen in the Stata code snippet, the process is simple. Generate the natural logs of your variables and then run the regression. Before jumping to robust errors, always consider if a transformation like this might provide a better overall fit for your data. To wrap up our session, let's distill these insights into 5 core best practices. First, always plot. The rvplot command is your first line of defense to visually identify the shape of your residuals. Second, test formally. Use estat hettest to provide rigorous statistical backing to your visual intuition. Third, default to robust. For cross-sectional data, using VCE robust should be your standard safety belt for valid inference. Fourth, check specification. Before jumping into complex modeling, consider if a simple log transformation can resolve the issue. Finally, model variance. Reserve commands like het-regress for when volatility itself is the central subject of your research. Always remember, heteroskedasticity is information. Don't just fix it. Take the time to understand what it's telling you about your data.